Welcome to this video lecture where we are going to see how to evaluate a Fourier series in an interval minus L, L. First, let us see the formula of Fourier series in an interval minus L to L, which is a general interval of period 2L. So this is the trigonometric series. A0 by 2 plus summation an cos n pi x by L plus summation bn sin n pi x by L. So remember in 0 to 2 pi we had cos nx and sin nx instead of n pi x by L. But it is very similar to that because here in the place of L, if we substitute pi, what we get? Cos nx and sin nx. So it is of the same form. That was for period 2 pi and this is for period 2L. And next we have the formulas for the Fourier constants A0, An and Bn. So learn the formula. This is specifically for the interval minus L to L. Now before going to the problems, let us have a glimpse on even and odd functions. So a function is said to be even if f of minus x is equal to f of x for all x. These are the examples, x squared and cos x. Similarly, a function will be odd if f of minus x will be minus f of x. And a few examples are x cube and sin x. And this is how the graph of the functions even and odd look like. For example, if you take y equal to x squared, it represents a parabola, and y equal to that was an even function, and next we have an odd function graph, y equal to x cube. So here again on the right side we have the differences between the graphs for even function and the odd function. Generally, when we consider functions, we may always think it has to be either even or odd. That is not the case. Let us see here. There are functions which will not be even or nor even odd. So when you have f of x, if it is not going to be equal to f of minus x, or if it's not going to be equal to minus f of minus x, and in that case, what's going to happen? Yeah, we can consider them as neither even and nor odd functions. These are the examples for that: e power x and x plus x squared. So here, if you observe, if you substitute x as minus x, for example, e power minus x, you are not going to get back e power x, or you are not going to even get minus e power x. So it is totally different. So this is a classic example for neither even nor odd functions. Now, why do we have to analyze about these even and odd functions? Because for even function, if we observe, the value of bn will be 0. Because the formula for bn was like 1 by l minus l to l f of x into sin nx dx. Sin being an odd function, and when a function f of x is even, totally we will have odd inside that integral sign, so that integral will be 0. So that is why we have bn 0 for a even function, and in that case the values of a0 and an can be written as 2 by l into 0 to l instead of 1 by l minus l to l. That minus L to L can be reframed as twice of 0 to L, since the function is even function. Similarly, when the function is odd, we will have a0 and an values 0, and bn value will be 2 by L 0 to L f of x sin n x by L dx. So this will actually reduce our work into half. Instead of finding out all the integration, that this, etc., we can just simply say like the value of bn is 0 whenever the function is even. Now let us start doing problems in this type. Look at the first one. Evaluate the Fourier series for the function 0 in minus L to 0, L in 0 to L. So when you observe this function, this is not going to be an even function, or it's not going to be an odd function also. So this is a type neither even nor odd. The Fourier series is given by all the three terms. We will have f of x equal to a naught by 2 sigma a n cos n pi x by L sigma b n sin n pi x by L. And we'll move on to all the formulas a naught, a n and b n formulae given by Euler's. First let us find a naught. What is the formula for a naught? 1 by L minus L to L f of x dx. And what is our function f of x given? 0 in minus L to 0, L in 0 to L. Now look at this. We need to split the integration minus L to L like minus L to 0 plus 0 to L because the function is given differently in these two ranges. So we have splitted the integration like this. From minus L to 0, the value of f of x is 0 plus from 0 to L, the value of f of x is L. Now let us integrate this. So it is just going to be 0 to L, L into dx because the first integral is going to be 0. So 1 by L into integral dx is x from 0 to L. And when we apply the limit, we get L minus 0 because in the place of x, we have to put upper limit L minus lower limit 0. Hence, the value of a naught is L. Now let us move on to find the next Fourier constant, an. This is the formula for an. 1 by L minus L to L f of x cos n pi x by L dx. Now as usual, this minus L to L integral we have to split into two halves. That is first one from minus L to 0, the function is 0 plus from 0 to L, the function is L. So we have substituted like this. Next, so this is going to be just the second integral alone will come because the first integration is 0. Now let us see how to integrate this. L and L getting cancelled, we have this term. Now remember, when we integrate cos, what we will get? Sine. Yeah. So cos, when we integrate, we will get sine ax by a. That is the formula. So here in the place of a, we have n pi by L. So that is a constant. So sine n pi x by L divided by, what is the constant? N pi by L. So that will come in the denominator from 0 to L. So now apply the limit. What is the upper limit? In the place of x, we have to put L. So we get sine n pi minus the lower limit is putting x equal to 0, what we get? Sine 0. And divided by n pi by L, I have written as L I have taken to the numerator. So the value is ultimately 0 because sine n pi is 0. Similarly, let us move on to find the last Fourier coefficient Bn, and this is the formula for Bn. As usual, split into two halves. From minus L to 0, the function is 0. From 0 to L, the function is L. So it will have just one term, L into sine n pi x by L dx. Again here L and L will get cancelled. So you get this, and when we integrate sine, what we get? Minus cos, right? So this, when we integrate, what we will get? Minus cos n pi x by L divided by that constant. What is the constant? N pi by L. Now we shall apply the limit. The upper limit is, in the place of x, when we substitute L, we get cos n pi minus cos n pi minus lower limit. What is the lower limit? In the place of x, when we put 0, we get cos 0. So the denominator by n pi by L, that L had gone to the numerator. Now remember the values of cos n pi and cos 0. Cos 0 1 and cos n pi is minus 1 power n. So substitute these values in Bn, we get 1 minus 1 power n divided by n pi. Now this is a very peculiar term, that is 1 minus 1 power n. Whenever we have such terms, we can observe it will be 0 either for odd integers or for even integers. So here in this case, this Bn term is getting 0 whenever n is even. So you can observe 1 minus 1 power n. When n is 2, what we get, 1 minus minus 1 squared, it's going to be 0. So likewise, minus 1 power 4, minus 1 power 6, etc. when it becomes, the value of Bn is going to be 0. And whenever n is odd, the numerator will become 2 divided by n pi. So we have all the values got, a0, an and bn. So let us substitute in the Fourier series. We have the Fourier series of f of x's. Remember the first term was a0 by 2. So L by 2 plus an is 0. So second summation is 0. Third term we have sigma bn sine n pi x by L. So in the place of bn, we are writing 2 by n pi. And of course, it is not n equal to 1 to infinity now. Since the values of bn are available only for odd integers, we are writing as n equal to 1, 3, 5, etc. till infinity. Let us do another problem here. Look at this one. Express the diffracted X-rays from the laboratory designed gas cell shown in the figure as sinusoidal waves over the interval minus 1, 1 of the horizontal base. Now consider actually X-ray diffraction first. X-ray diffraction is very much useful nowadays in many fields. So all of you would have been already knowing all these. Just a few points, let us refresh on this. So X-ray diffraction is widely used in to identify crystalline materials like minerals, inorganic compounds, etc. and in thin film analysis, and then to identify structure of materials in biology and chemistry like vitamins, drugs. To identify their structure it is used, and similarly to determine the size of atoms, the lengths, the type of chemical bonds, the molecular formula. Everywhere X-ray diffraction is widely used. I've just told some few. There are many other applications of X-ray diffraction. So here what exactly they are asking. So given this particular sample of X-ray diffraction, they have asked us to convert the X-ray diffracted rays into sinusoidal waves. So first observe the path of the diffracted ray in the picture. Can you identify the graph to which graph it is equivalent? Because first we need to identify the function for which we need to represent as sinusoidal. Yeah, it is exactly this one. Are you able to identify now? Yeah, this is the graph of the function y equal to modulus x. So the diffracted X-rays are represented by the function y equal to f of x, which is modulus x. So our work now is to find the Fourier series of mod x in the interval they have given minus 1 to 1. So like this, we have to represent the diffracted rays but with sinusoidal waves. When we observe this particular function mod x, it is an even function. So for an even function, what we learned, yeah, bn will be 0 for all n. And the formula for a0 and an also will be a little bit different here. You remember that. Now comparing the interval minus L to L with minus 1 to 1, here specifically we have the value of L as 1. So the Fourier series is given by f of x equal to a0 by 2 plus summation an cos n by x by L, because there is no bn term here since bn is 0. Hence, now replace the value of L as 1. We have like this. Now we'll move on to the formulas of a0 and an. So let us start finding a0 first. This is the formula for a0. Remember, because since we need to substitute f of x as mod x, and we cannot integrate or differentiate modulus x. So before that, we need to replace mod x in other form. So this is the definition of modulus x. If you remember, it is going to be plus x in the positive range and minus x in the negative range. So in the place of f of x, we shall substitute just plus x, since the modulus x is plus x in the positive range, and since we are integrating from 0 to 1, we are integrating only in the positive range. So f of x is x. And of course, it's a simple integration. X, when we integrate, we have x squared by 2. Now apply the limit. 2 into 1 minus 0 divided by 2, the answer is 1. Hence, the value of a naught is 1. Next, we'll move on to finding the value of an. This is the formula for an. And as usual, substitute the value of f of x as x, because what is f of x? Mod x, but it is going to be plus x in the positive range. And we are putting L equal to 1. And look at this term, how we are going to integrate this. Yeah, it has two product terms, x into cos n pi x. So let us remember our famous Bernoulli's rule. Keeping the first x term into integrate the second. So what is the second term here? Cos n pi x. That when we integrate, we get, yeah, sin n pi x divided by n pi minus differentiate the first. So x, when we differentiate, 1 into integrate the second. When we integrate the second term, what is the second term? Sin n pi x. That when we integrate, what we get? Minus cos n pi x divided by n pi. Already n pi was there, so one more n pi will come. So totally we will have n squared pi squared. Of course, the differentiation integration is over, because the next will be when we differentiate the first term, we have here 1, when we differentiate 0. So the integration is over. Now we have to apply the limit from 0 to 1. So what is the upper limit? In the place of x, we have to put 1. So we have like this. So we have just substituted x as 1 minus the lower limit. What is the lower limit? In the place of x, we have to put 0. So we have like this, because sin 0 is going to be 0, cos 0 is going to be 1. So remember these formulas always. Sin n pi, 0, cos n pi, and minus 1 power n. So substituting these values, we have the answer of an as 2 into cos n pi minus 1 divided by n squared pi squared. So we will have like this. And now you can replace cos n pi as minus 1 power n. And already we have learned, whenever we have 1 and minus 1 power n together, like this, minus 1 power n minus 1, it will either be 0 for odd integers or for even integers. In this case, 2, 4, 6, etc. when you put, you get plus 1. So 1 minus 1 will be 0. So an answer will be 0 whenever n takes even integers. So that is why we have like this. And when n is odd, we will have in the numerator minus 2. So totally minus 4 divided by n squared pi squared. Hence the Fourier series of modulus x can be written as f of x as a naught by 2. Our a naught value was 1. So 1 by 2 plus sigma an cos n pi x. This is the answer of an. In the place of an, we write minus 4 by n squared pi squared. And of course, the summation, we cannot write 1 to infinity now, because an is having value only for odd integers. So we specify n equal to 1, 3, 5, etc. So which gives the sinusoidal waves. So thus we have expressed or represented the diffracted X-rays, which was in the form y equal to modulus x, as a cosine series, that is the sinusoidal waves, using our Fourier series technique. Now let us move on to the next problem. Here, finding Fourier expansion of x minus x cube, we need in minus 2 comma 2 interval. Now look at the function f of x equal to x minus x cube. If you replace x as minus x, what do you observe? Minus x plus x cube, and when you take a negative sign, we observe f of minus x is minus f of x. What does it say? Yeah, f of x is an odd function, because do you remember, whenever f of minus x is minus f of x, that function is an odd function. And whenever we have odd function, the values of the Fourier constants a0 and an is going to be 0. So we just have a very simple expression of Fourier series as summation bn into sin n pi x by L, because here we have a0 and an values are 0. And now let us move on to finding the value of Bn. Before that, the interval comparison let us do. Minus L comma L is our general format, but here in this problem specifically they have given minus 2 to 2. So comparing these two intervals, we have L equal to 2, and hence f of x formula becomes like this, just substituting L equal to 2. Now we'll move on to find the value of Bn. This is the formula for Bn for even and odd case. So since this is an odd function, we have formula like this. And now let us substitute in the place of L 2. So the value of Bn is this integration. Again here, if you look at the integral, we have product of two terms in the integrand. So we have to use Bernoulli's rule as usual. And before going to the Bernoulli's rule of integration, let us have a glimpse of the basic formulas. Sin nx when we integrate minus cos nx by n, and cos nx when we integrate we get sin nx by n. Now let's start the integration. Bn equal to, what is the first term? X minus x cube. So just keep the first term into integrate the second. Sin when we integrate we get minus cos n pi x by 2 divided by n pi by 2 minus differentiate the first. Now what is the first term? X minus x cube. That when we differentiate we get 1 minus 3x squared into integrate the second. So minus cos when we integrate we get minus sine divided by, again n pi by 2 will come. So totally we will have n squared pi squared by 4. Now what will be the next? Plus differentiate the first term. So what is the first term here? 1 minus 3x squared. So that when we differentiate, what we will get? Yeah, minus 6x. So the next is plus minus 6x into integrate the second. So second we have minus sign. So that when we integrate, what we get? Yeah, sign when we integrate minus cos. So already we have a negative sign here. So we will have minus cos. So it is plus cos n pi x by 2 divided by, again n pi by 2 will come. So we will have n cube pi cube by 8. Next, minus differentiate the first. So here what is the first term? Minus 6x. So that when we differentiate we get, yeah, minus 6 into integrate the second. So cos when we integrate we get sin n pi x by 2. Again n pi by 2 will come. So totally we will have n power 4 pi power 4 by 16. And that's all. The integration is over because we have got the constant on the first term. So the next, when we proceed, when we differentiate the first term, what we will get? Yeah, 0. So now we have to apply the limit. So before applying the limit, remember these formulas. Sin n pi is going to be 0 and cos n pi will be minus 1 power n. So when we apply the formula, these formula, when we use, the value of Bn will become upper limit. In the place of x we have to put 2. So the first term will be 2 minus 8 into, when we put x as 2 we get minus cos n pi divided by n pi by 2. So that 2 I have taken to the numerator. Next will be 0 because sin n pi is going to be 0. And the next term will be minus 6 into x. No, there we have to put x as 2. So minus 12 into cos n pi by n cube pi cube by 8. So that 8 has gone to the numerator. Next plus 6 into 0 because sin n pi will be 0. Minus lower term, lower limit. What's the lower limit? When we put x as 0, the lower limit will be 0. All the terms will become 0. So this is the final value of Bn when you simplify. Hence the Fourier series of f of x is given by f of x equal to sigma, what we had, Bn into sin n pi x by 2. So in the place of Bn, just substituting the value of Bn, we have this. So students, I hope you would have learned how to evaluate Fourier series in an interval of the type minus L comma L. So kindly use the techniques what you have learned in the lecture and try these problems. In this lecture, we learned how to evaluate Fourier series of functions having a period 2L, especially in the interval minus L to L. And the next class, let us go to learn half-range series problems in the interval 0, pi. Thank you.